All right, so, problem set 9 is due tomorrow midnight. We'll have a final question and answer session at the problem session tomorrow. And I'll put up the final problem set, which is due a week from Tuesday. That's the Tuesday before Thanksgiving. Okay. And I hope everyone's thinking about their final projects. And so I would like to see your abstracts next week by Wednesday. Okay, you can send it to me anytime, but I'd like to see them by then. All right, so let's see if we can conclude this final part of this story about coherent interference, correlations, and photon statistics, something we've been talking about for a number. So again, try to set the stage here. So when we think about coherence, the way we often think about measuring coherence as the capability of interference is seeing how a wave is correlated with itself at different times, if we're thinking about temporal coherence. So we've had this sort of first order correlation function. We call G1, correlating the field with itself at two different times. And classically, we're correlating E with E star at two different times, where this symbol in this context means a average over some classical probability distribution. Of the field with itself, okay? And that's the kind of thing that this kind of first order correlation function, we measured in an interferometer. So in that, we looked at Mach-Zehnder interferometers, and my rate here of absorption of the was given by, depended on the intensity at that output port, which is that correlation function. And this intensity at this output port depended on the electric field in these two ports and gave us that autocorrelation function, which we wanted to measure, okay? So in this context, we thought about the field interfering with itself at two different times, and that interference we saw through these two different paths. Yes, me?
For the correlation function, should those both be T?
In this case, they're both T, but of course, this guy is this squared, where the electric field at the output port is the superposition of the two fields associated with the two paths, and it's when we square that we get the 2-time correlation function. So we're looking at the intensity at this time averaged over the probability distribution, or equivalently long time average, but that intensity depends on the superposition of the two fields, which is how we got this 2-time correlation function. Okay, excellent. Right, so that's the classical description. Quantumly, instead of thinking about absorbing classical wave intensity, we can think about absorbing those energy in discrete quanta. So we can think about that rate of absorption instead as a rate of photon counts. And it's effectively the same expression from the Glauber theory, where instead of having the average taken over a classical probability distribution. More generally, we have the trace with the quantum state of the field, whatever that is, where this intensity operator is the quantum equivalent of the square of the amplitude, which is, instead of E star E, I have E minus E plus with hats on them. And this is my intensity operator. And my intensity operator is associated with the absorption of one photon, okay? But I can have many in the field, but each photon is associated with an annihilation operator, which is this, okay? So that's what we had. This is about single photon counting and counting many, many of those photons at the same time, okay? And in particular, if we have a coherence state, a state which is a eigenstate of the annihilation operator and thus an eigenstate of E plus, so this is a coherence state. Everyone clear on that? Then in this case, so, oh, by the way, this function G1 of T1 and T2 is the quantum generalization of what we had before. This is the G1 correlation function in quantum land. If I have a coherence state, then what is G1 at T1 and T2 if I take this expectation value? It's just, I would, this is backwards. Now it makes sense, okay? So if I take this expectation value, E plus acts on the state, gives us back the complex amplitude, and this gives us this conjugate. So this is just E star E in that case. So for a coherent state, the correlation function factorizes. I'm going to come back to that point and emphasize that this is factorizing the product of two functions, one at T1 and one at T2. And if I have a statistical mixture, of coherent states, so my state is a statistical mixture weighted by some probability distribution, then what is the G1 correlation function for this state when I take this expectation value? For the coherent state, I just have this, right? Now when I have this, what do I get? Same integral. So this thing, if this is this guy, the G1 function, it's just a statistical mixture of those things. Does everyone see that? So we recover the classical theory when we have a statistical mixture of coherent states. And this is what we're calling classical light. Light that cannot be written this way, and we'll talk a little bit more about that today, what features that kind of light has, cannot be expressed this way. For the very, if the probability distribution is not a delta function in function land, it doesn't factorize. The factorization is associated with the fact that there are no fluctuations in the field. The field is just that amplitude. If there are fluctuations in the field, then we have some probability distribution, and then we have some extra fluctuations. We wouldn't have the correlation function would not factorize it. The lack of factorization is in this context associated with excess fluctuations. Okay. So when we talked about the photon count, so this is all a kind of thinking about this from the point of view of coherence states and what we call the continuous variable basis of the field, but we can also think about it in terms of photons. Okay. And when we thought about it in terms of photons and the thinking about this in terms of the discrete variables, well, it was useful for us, as we did last lecture, to think about temporal modes when we're thinking about this kind of detection in some kind of detector with some kind of beam coming in, which has some spatial mode, some transverse area, say associated with a Gaussian beam. But in addition, I'm counting in a certain time interval, and I thought about temporal modes. The volume that defines the quantum field now is determined by a duration in time. C times delta t is kind of the length of the mode to there. So that's an important concept, the concept of a temporal mode. With that said, what we did is we said, oh, I can then write my intensity operator as a function of time, quantized not relative to energy, but relative to flux. So we instead had the energy or the intensity of the field, which is the energy per unit time per unit area. So that's that times what we call n dot, where n dot is the rate of photons coming in per unit time as a dagger A, where these guys have units now, the unit of 1 over the square root of time, so that this whole thing has the units of 1 over time, the number of photons per unit time. And in that case, my G1 correlation function, say at the same time, is, proportional to n dot. It's the rate of photon counting. Okay, so instead of thinking about how much energy is coming in per unit time, I'm thinking about how many photons come in per unit time. Yes, babe.
So this isn't a correction, it's an honest question.
Yeah.
Should the creation and annihilation as function of time there have dots over them? Because
No, so that's what I was trying to say. These guys have units. They have the unit as, by definition, of per root time. So that a dagger day A has a unit. So this is in the same way as we think about the wave function having units in space, right? So this thing, this is just by definition, in the same, when we think about a Dirac delta, it has units in it. So when I say A of t, I'm saying A in an infinitesimal time per unit root t. That's what that means. Yes, Nate?
Because of that Computer relation,
Yeah.
does that mean that there is no, because the Computer between n dot and n would be 0, would that
Right, that's because this is per unit time. If I haven't integrated, so the integral of this over some time interval is equal to n in that time interval. Okay, this is per unit time. If I integrate over time, this is the number of photons in this chunk. But if I shrink that to 0, it's 0. Okay. Right. So again, this is a dagger. I can think about photon counting as what was the intensity now is a dagger A, but I've done it per unit time. Okay, so that connection between the amplitude and the annihilation operator of a discrete photon and the energy or the intensity of the number of photons is an important translation to make between the classical field and the quanta of the field. Okay, so if I have, it's just another way of saying this, if I have a coherent state now, which I'll write relative to this normalization. So, you know, if I divide this by this, make the square root of t, that's the electric field strength, so that this is dimensionless. So by coherent state, I'll call it alpha, such that the expectation value of this is alpha squared, right? So A on this gives me back the eigenvalue. So everything now here is in continuous time. Alpha squared doesn't represent the number of photons, it represents the rate of photons, okay? So if I integrate this over a certain time interval, that tells me the average number of photons in that time interval, okay? Just like psi star psi is the probability density to find the electron per unit length. Now I'm thinking about it per unit time. Is that clear? Be confusing, okay? So if I have a coherent state of that form, then G1 of with itself, which is the expected value of n dot, is that, just as we had classically. And importantly, the interference that I saw over here in the classical picture that we discussed before is seen equivalently in the quantum picture, but now just replacing A by its eigenvalue, I get back exactly to the classical story. And the field amplitude interfering with itself is seen in the fully quantum model as well, as long as I'm dealing with the coherent state. Now, equivalently, I can think about a single photon state. Let's say a single photon wave packet, where I create one photon in the wave packet I'll call phi. And a dagger of phi is the creation operator that creates a photon in that wave packet according to this formula. Okay? So you can think about A of t without that as this being a delta function at some time. So it's like creating it in a time slice eigenstate, in the same way that a position eigenstate is a delta function in space, something which is a delta function in time which corresponds to creating a photon at that time. This spreads out the probability density in that way. And in that case, G1 of t is y.
Scaled by 3.
It's this. It's what we did last lecture. It's the square of the wave function. That's the probability per unit time to see that photon. So these functions look exactly the same. In this case, when I go back to this interferometer, I'm putting a single photon wave packet. I would see over out here the wave packet output would be the superposition of the two wave packets interfering with themselves, and when I square that amplitude, I'd see the amplitude interfering with itself. That's exactly the same thing as the classical description we had, but this here is for a single photon, represents the probability. Here, I can think about this in the following way by writing alpha as the displacement operator acting on the vacuum. And alpha, in this case, would be related to this particular, I've created this in this particular wave packet, has the following form as we discussed last time. Where I defined alpha of t as n bar of 5, where n bar is the mean number of photons in the whole pulse. So this is the rate at which I would see photons per unit amplitude integrated over to all times is the total mean photon number. So the point I'm trying to emphasize here, n bar over 2, this is the square root. Someone told you to memorize that and they got it all wrong.
Me too.
Okay, now it's right. This is the problem. The point I'm trying to make here that we discussed last time is that the coherence state is associated not with a definite number of photons, but every photon is in the same mode. In this case, every photon is in this wave packet defined by the shape of the pulse. It's just normalized relative to that. Yes, Tom?
Need a Fock cat on the right hand side?
We do, at times n in that mode. Absolutely, thank you very much. Yeah, my mind is not completely screwed on. Yes?
So the difference between then these two quantities, alpha magnitude squared and phi magnitude squared, is that alpha magnitude squared is necessarily locked to a single mode?
The difference here is phi is the probability amplitude for a single photon. Alpha is the complex amplitude of the coherent state, but they're related just in terms of the normalization. So the square of this amplitude over here, which we wrote over here, the square of this amplitude here, so I've written alpha of t as the square root of n bar 5t. That is to say, phi of t represents the probability density or probability amplitude, phi squared is probability, for seeing a photon in at a certain time. Alpha is the eigensiv, the annihilation operator, whose square represents the mean photon number. But the point I'm trying to emphasize is that the coherent state is it's different from the single photon state in that it has an uncertain number of photons, but every photon is in the same mode. So in this picture that I was getting at over here, I can think about this as a coherent state pulse that I put into this interferometer that interferes with itself. But every photon is in that wave packet. I just don't know how many there are. There could be 0, there could be 1, there could be 2. The probability of seeing that number of photons is determined by the Poisson statistics, but every photon is in the same mode. I just don't know how many photons there are. The interference that I see classically, I can understand as quantumly the probability amplitude of every individual photon is interfering with itself. And what I see at the end of the fraction of the intensity comes out here or here is understood by the probability that that quantum of energy appears here or here according to quantum mechanics, described completely by the quantum mechanics of a single photon interfering with itself. Yes?
So, you mean if my coherent state has a particular wave function,
Yes,
all the photons also have the same wave function?
that's correct. All of them have the same wave function. That's what I'm trying to say here. I've created n photons in that mode. So I wrote the state 1 phi, that's this, the state n phi is a dagger of phi to the power n divided by the square root of n factorial acting on vacuum. So this is n photons in that mode. I'm labeling them by phi. Before we said sub k. That was the mode in a cavity. Now I'm just calling it a wave packet. So every photon's in the same mode, I just don't know how many there are. Yeah, Nate.
Does the racing wave packet upper have the time dependence?
These have no units, right? Because this has units of 1 over root time, this has units of 1 over root time. So this is in that mode. This has no units.
But doesn't alpha have a time dependence? So if that's how you define the state alpha, where's the t come from?
So if I look at A of t acting on alpha, this thing has units. And this gives me that. This has units of 1 over root time. This has units of 1 over root time. Great. Okay, good. So now we want to turn our attention to Hanbury-Brown twist. So now we have second order coherence / correlation. Okay, so we looked at this problem. Where instead of having an interferometer where we have two paths of that the wave can propagate along, where we recombine and then look at the interference between them, we're just correlating the intensity with itself at two different times. Okay? That's what we see in this kind of tube armed with two detectors. Now I have two detectors, or square alarm detectors. Which is the integral over the probability distribution, classically, of the intensity, which is E star E at time t1 and E star E at time t2. Okay. And in particular, if we looked at this as for a stationary source, like we have with thermal light, what we saw was this G2 correlation function as a function of tau, where tau is the time difference between these two different times. And for a stationary source, it only depends on the time difference. It doesn't depend on the origin of time. We saw this, right? Where this, for a long time, gave me the product. It decorrelated. I just had the product. And for a stationary source, that's this. And at 0 time, this was equal to that, which for a thermal source is that. Okay? So what the Hanbury-Brown twist interferometer does is it's looking at the difference, in a sense, between the average of the product and the product of the averages. Sometimes known as the covariance, if you want to say this, right? And when tau is sufficiently long, this goes to 0. But at 0 time, I have excess fluctuations. And we remember from our studies of the thermal state, this factor of 2 was associated with the intensity fluctuations, okay? And so the intensity fluctuations have only a certain coherence length or coherence time, and so I can measure the coherence time of the source by looking at the correlation of the intensity fluctuations rather than the correlation of the field with itself, as was written up there, okay? Very good. Now, question for you. If instead of putting thermal light, I put on a laser on this, and I looked at this, so for a coherent state, what would this look like? Or just a classical wave that had a well-defined electric field, in that case, what would this look like in that case? A flat line, right? So for a coherent state, it's this. Because again, in that case, there are no intensity fluctuations. What this is measuring is the intensity fluctuations. If there are no intensity fluctuations, then this correlation difference is zero. And this will always be, so for a coherent state, or then my G2 correlation function is just the product of the intensities. It factorizes. Again, factorization is important. That means that there's no fluctuation in the intensity, and I would see this flat line. Okay. Another question I have for you. This is a very subtle point. Maybe you will catch it more than what I told you. Suppose I take this source and I put a very narrow band filter. So it's just making this field more monochromatic, okay? Now, if I had a CW laser code, monochromatic laser, it wouldn't change anything here. But what would happen to, if I have a sodium lamp, and it's not a coherent source, it's a thermal source of light, but I just put it through a narrow band filter. Well, my first order coherence will improve, right? I mean, those fringes that we saw over here where we looked at this first order correlation function, we saw that. This, I would see a longer coherence length, right? Because I've made the field more monochromatic, right? But what about here? What would happen to this? If I looked at the sodium light, what would happen? So the question is, remember the coherence length, or the coherence time, how fast is K, is sort of 1 over the bandwidth. It's saying something about how much bandwidth. So if I increase the coherence time, let's say made it more monochromatic, I would see this decay less, but it would still have a G2 because it doesn't change the intensity fluctuations. The intensity fluctuations are not changed by that because the intensity fluctuations are related to the more than one photon kind of effect. The single photon wave function is affected. The single photon wave function is affected, and thus I get a long coherence time. But the statistics, the fluctuations are not affected. So we would say a monochromatic field has first order coherence, but not necessarily second order coherence. A coherent state, on the other hand, has both first order and second order coherence. Because if I had a coherent state, I'd still get this flat line. That's why the coherent state is called the coherent state, because it has coherence at all levels. We'll talk about the nth order coherent state. That's why Glauber called the coherent state, because it's coherent at all levels. All right, so now I want to talk about the quantum description of this. So intensity correlations are now about photon-photon correlations. They're not about the first order thing, which is about an individual photon, and that individual photon may take different paths, but there was nothing about correlations between photons. It was about counting one photon or not, and whether it's there or not had interference effects, because the single photon interference itself, but it's not in any way related to the statistics of the photons. But when I start measuring photons at two different times, I'm asking about photon-photon correlations, okay? And the photon-photon correlations are seen in two photoelectric, so we have this picture of, on here in the continuum, and the electron causes an avalanche photodiode to click, so I have two different photoelectrons coming off, and the detection of those is my joint detection of two photons. And the rate of this coincidence, or photon-photon absorption, is in a similar spirit to what we talked about with the single photon. Using Fermi's golden rule, well, I'll call this ground 1, excited 1, ground 2. There are two different atoms in my two different detectors that initiate this effect. And by Fermi's golden rule, I have to go from the initial state to the final state. So there's some final state of the field, both electrons get excited, and then there's some interaction that's associated with absorption and the positive frequency component at time t1 and time t2 that takes me from the ground state in the two atoms for some initial state of the field. So that's the most important point of this, is that it's a two photoelectron effect, which is associated with the absorption of two photons and the raising from the ground state to the excited state, and from some initial state of the field to some final state of the field. But as before, I have to sum over the final states of the field, because I'm not actually measuring that, I'm only measuring the electrons.
Are those two different Hamiltonians, or are those?
They are.
Okay.
So this comes from expanding e to the minus I ht to second order. So in usual time-dependent perturbation theory, we're only doing first order, but this is a second order effect. So it involves two Hamiltonians. That's where that came from. Okay? So, and each one's associated with the two different atoms. At the end of the day, these guys involve a d dot e and a d dot e, so this involves the sum of final states This is the important point here, is that this event that we're measuring, associated with two different photoelectrons being generated, is associated with the absorption of a photon at time t1 and a photon at time t2. The absorption is the annihilation operator. That is to say, it's associated with the removal of a photon, and that's the positive frequency is where this came from. So when we write it times its complex conjugate, and we sum over the states in the same way we did last lecture, remember that, Arika, we were talking about that? We get the expectation value associated with whatever the state is, E minus T1, E minus T2, E plus T1, E plus T2. Yes, sir.
Just to understand it physically, so two different atoms, but they're coupling to the same quantized radiative field at different times. Is that the way I should think of it?
That's right. So in this picture, there are two atoms that are initiating my avalanche photodiode to cause a photon click. So that's associated with they're both interacting with the field, and one goes click at time t1, and one goes click at time t2, which is actually the rate.
Thank you.
Yes, Donald next.
Was there a missing superscript on those E's?
Yes, this last guy should have a E plus, E plus, E minus, E minus. Yep, thank you. Nate, you had a question?
Because now it's two separate atoms, is it possible that T1 and T2 are equal?
Yes, absolutely. They could be equal. I'm not saying that they're equal, I'm just saying this is a more general thing. This function over here is a little bit different than the one over here, but what this represents is the following. This whole thing is the expectation value of I at T1, I at T2, normally ordered. This is called G2 of T1 and T2. So classically, that's what we had. This is what we call G2 at these two different times. It's the correlating the intensity with itself at two different times. Quantumly, I have this. This formula looks like that formula, but it's got some fanciness to it. Fancy. Look at all these symbols here. This has hats on it. That didn't have hats on it. And it has this colon. What the heck does the colon represent? The colon is what we call normal order. So, the normal order of that is the normal order of the intensity operator, which is E minus E plus times E minus E plus at time t2. Okay, so I just substitute in, this is the intensity operator at time t1. This is the intensity operator at time t2. What does normal order mean? It means forget about the fact that you don't commute, put all the things with the dagger on the left and all the things with the non-daggers on the right. And the normally ordered version of this is E minus at T1, E minus at T2 times E plus at T1. Everyone clear on that? Yeah.
So the E pluses are the ones
With the annihilation operators.
wait, okay, yeah.
And the ones with the minus have the daggers. Okay. Right? Yeah, it's kind of backwards, but say loudly. Okay? So, that's what this means. We got it from this because it started here. The normal order came from this. We annihilated two photons, so they had two annihilation operators on the right. But it's not just the intensity operator, it's the normally ordered version of the intensity operator that appears in the rate at which these things happen. So Glauber derived that. So that's the thing that is actually being measured in the detector. Question. Suppose the state, the input initial state of the field, were a coherence state. This is a state which is a eigenstate of E plus with eigenvalue of the electric field. Suppose that were true. In that case, what is this?
The classical.
If I put this state in here, it is the classical. So what actually is it? Right, but it got all the times in there. Yep, but you're right, Andy, but just with all the times. So it's that, which is the product of the intensities. It's just what we had classically. So this form of the G2 correlation function recovers the classical thing when the field is coherent state, as it should. And moreover, if I have a statistical mixture of coherent states, then what is G1?
Weighted by the distribution.
It's just the same thing, weighted by the distribution. So I get back Hanbury and Brown and Twist from the fully quantum theory. There's nothing different. If this were a Gaussian distribution, then I'd get back that nice picture as we had from Wick's theorem and the like. So I get back the classical theory in that case. Yeah.
So many times earlier in the course we were like, oh, the photoelectric effect isn't the reason we need a quantized field and everything. Is this the reason? Hanbury, Brown, Twist?
No, not yet, because I can completely explain Hanbury Brown Twist with a classical probability distribution that was Gaussian. I didn't need no sticking hats and operators and nothing. This Hanbury Brown Twist were radio astronomers who knew nothing about photons. They knew about radio electronics and homodyne detection and noise, and they said this is how we should measure it. And the physicists had conniptions about it because they said, how do I understand this from a quantum field theory? When you and Glauber saved the day and won the Nobel Prize decades later. But, well, 40 years.
So have we gotten to why we need a quantized field?
Well, no, we're about to. Okay. So, well, we did one example, and so, and that we did this kind of. Remember, we talked about Aspect, Grandier experiment, and heralded photons, right? When we didn't have a coherent state over here, but we had a single photon state, a coherent state or a statistical mixture of coherent states, then we saw something weird. Okay, we'll come back to this in a moment. Okay, so, right. So, I finally want to say, I can think about the nth order correlation function, which you're like looking at in your homeworks, if you looked at that, where I have more beam splitters and more detectors. This is I will measure a third order correlation, and then I can measure a fifth order correlation function, blah, blah, blah. They're all going to be associated with simultaneous detection of multiple photons, and the G, I'll get to your question in one moment, Kristen. The Gn correlation function in that case is that. Okay? Yes, Tristan.
So the way that you have it on the homework is you have a split and then another split on for an example of the n=4 case.
Yeah.
Do they have to be split in certain ways to make sure it works out, or is it just whatever
one has to be careful about the retarded time, so that, you know, if this, there's a, you know, if that beam splitter, I'm saying this is measuring G3 at 0, but really it's G3 at this retarded time, that retarded time, that retarded time. I have to adjust, but that's not so important for work. I'm trying to get, in the homework, we're looking specifically at Gn at 0, which is associated, so if I looked at G2 at 0, right? So it's associated with the correlation of a photon with itself at the same, it's a photon correlation at time equals 0. But the configuration there is just to say, how would I measure that? The details of how much time it takes to get here and how much time it takes to get here and how much time I'd have to take that into account. But at the end, I'm essentially measuring this, unless I have some time delays and such.
Is it the same as to say all of T1 through Tn is the same equal?
That's for all.
Oh.
Yeah. Okay, good. Where were we? Oh yeah, here is where we were. So, for a coherent state, what is this?
E minus 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 E plus plus plus.
Yeah, I just replaced, because remember this is really E minus T1 dot 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 E minus Tn E plus T1 E plus T2 dot 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 E plus Tn, right? And when I put the coherent state in, every one of these guys gets replaced by its eigenvalue, and I get back just the classical thing. Just a product, and I get something which factorizes. Okay, so, and if I had a statistical mixture of coherent states, I would just integrate this with the probability distribution. So once again, I get back to classical story. But the point about the factorization here is going back to a thing we've discussed many times, which is that for a coherent state, we have a Poisson process. Which is to say, the joint probability or the joint rate of detecting at different times factorizes. They're statistically independent from one another. That's why the annihilation operator gives us the Poisson statistics in the end. If I annihilate a photon at one time, it doesn't in any way affect what I'm going to see at a later time. Okay? That's what's special about coherent state, because it's this weird relationship between the classical amplitude and the annihilation operator and the statistics associated with that. Okay. So in a coherent state, if I have a coherent state detecting a photon at one part of the pulse, in no way affects my ability to detect another photon pulse. In fact, if I have a coherent state, which is in this pulse, it's a product state of coherent states in those little pulses. The big coherent state is a product state of the little coherent states. If I had a single photon state, well, that's not true. Because if I detect a single photon here, I'm not seeing it anywhere else. A single photon state in the big pulse is actually 0,0,0,0,1 plus 0,0,0,0,1,0 plus dot 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 divided by the number of this. It might be in this pulse, it might be in that pulse, it might be in that pulse. So if I detect it in the first one, I'm definitely not going to see it in the other ones. So in this sense, the single photon pulse is entangled between these different, we'll come back to that whole, that's a very complicated business. Yeah,
So you're saying if I have a coherent state that's evolving with time, and if I detect a single photon, in the future it doesn't affect the state?
that's correct. What I'm saying is, there's some, in each of, what I'm saying, it's not that I don't affect it, it's that the probability, each one of this pulse will have, if this thing had a certain number of photons n, 1 over n of them on average is here. So it doesn't affect whether I'll see the photon, it affects the probability, right? So if I see I may see a photon in here, I may not see a photon in here. The probability I see a photon or not, or the number I see, is given by Poisson statistics, okay? And those Poisson statistics are determined by the average number of photons in that mode, okay? The average number of photons in this mode is the same as the average number of photons in that mode. So if I see you know, the thing about a coherent state is it has an uncertain number of photons. So if I see one photon here, I still have a chance of seeing one photon there. Because at every one of these time intervals, there's a probability of seeing an infinite number of photons. It's small, but there's no correlation between them. Yeah?
So, overall, is having a coherent state and knowing the number of photons you have mutually exclusive?
Correct. A coherent state has an uncertain number of photons. What's the uncertainty? If I have a mean number of photons n, what's my uncertainty in it? The square root of n. So a coherent state doesn't have a definite number of photons. But what's important is the coherent state in this big mode is a product state of coherent states in the little modes.
Unless you're in the ground state.
Is that?
Unless you're in the ground state.
Unless you have a vacuum state. If you have a vacuum, well then, yes, there's no chance of seeing a photon anytime at all.
So can you technically not call a vacuum state a coherent state?
No, it is. It's a coherent. It's the only state which is both a Fock state and a coherence.
Eigenvector annihilation.
And that's right. So and the eigenstate of the number operator at the same time. Okay. So the single photon state, in a sense, was an example of that. Something that Benny was asking about. That is an example of something I really need the quantum theory for, and we can be more formal about it now. Okay? So, I want to talk about photon bunching and anti-bunching. Okay? So let's look at this experiment again, the Hamburger-Brown twist type experiment, with some time delay here, and some coincidence counter. Okay? So my G2 correlation function is that. And from a photon point of view, this is associated with counting photons in the first time interval and in another time interval, such that I see, it's the joint probability of seeing photons in time t, time t. I really need to integrate over time windows to make this thing a number rather than a square of a rate. so I would integrate over some time. But this is about one photon being clicked. So what this coincidence counter does is says, what's the probability of seeing some photon come at time 0 and another time come at a later time tap? Does everyone see that? That's what this is. This is looking at that correlation. A photon arriving at time 0 and one that arriving at a later time. If they both arrive at the same time, we say those two photons are bunched. If they are unlikely to come at the same time, we say the photons are anti-bunched. Okay. Now, classically, we have that. Okay. So this kind of integral, I can think about in the same way that we think about wave functions and wave mechanics as a kind of inner product between these two functions. Because I can write a square root of this and a square root of the probability there and put that together, and it's like taking two functions, multiplying them together, and integrating. We know from our studies of special functions work that's like an inner product over function space. So I'm going to write this as the inner product of the intensity with itself. And that inner product is defined relative to my inner product of, that's my Braun-Ketz, okay? Okay, now here's something that's interesting. If I look at that inner product, the magnitude of this inner product, this thing has to be less than by, so, oh, let me, I have two vectors, v1 and v2. The magnitude of the dot product between those two vectors is less than the magnitude of v1 times the magnitude of v2, or equal to, unless they're the same. That's the Cauchy-Schwarz inequality, right? So what does this say? That says that this is equal to, or less than or equal to, the square root of the length of this vector, which is the inner product of it with itself. The square of the amplitude, that's it. Which is equal to the square root of G2 of 0, 0. And this is the square root of G2. And if it's a stationary process that's independent, then it doesn't matter as long as they're at the same time, that's like G2 at 0. So this is equal to G2 at 0. This was G2 at tau. They're all positive numbers, so I don't need the absolute value. Yes?
Why do we have to include the square root of p in your inner product?
I did. That's my definition. I'm saying the way I calculate the inner product is I take the two functions, weight them by that probability.
I see.
That is an inner product by all the rules of the inner product. So I'm defining the inner product as that particular integral.
I see.
Thank you. Okay, but look what we found. This tells me equivalently, meaning the joint probability of seeing two photons at the same time is always bigger than or equal to the probability of them seeing them separated, which is to say that photons are bunched. They could be not bunched only when this is equal, so which means that the probability of seeing them together is the same as the probability of seeing them at any separated times when at equality. And under that, what is the condition under which that is true, when this is equal, given all we said?
So coherent.
When I have a coherent state. If I had a coherent state, then it wouldn't make a difference, right? Because then the two, it would factorize. So this is true for a coherent state. Otherwise, the photons are bunched. Or aren't they? There was a sleight of hand here, which is that I assumed this, that this was a positive probability distribution. It could be, for example, thermalite. As we saw here, G2 at 0 is twice as big at G2 far away because, well, that was what happened when we had thermalite. So for thermalite, we have bunching, okay? But if my state cannot be expressed as a classical Cisco mixtures, then I can violate this. And that's what we saw when we were talking about so if I have this kind of thing where I have coincidence, okay, then if I put in a single photon state over here, and I looked at my coincidence counts, what I would, so this, we saw this for thermalite. This we saw for the coherent state. Non-classical. This is my G2 as a function of tau. When tau is together, when tau is 0, what's the probability of coincidence? If I have a single photon? 0. Because the photon either goes here or here. And so I will see nothing. Okay? Of course, if I make things bigger, if I have a whole string, so I have a single photon emitter that emits exactly one photon, then they're perfectly anti-bunched. There's no chance of seeing two photons in there. If they are separated by a certain amount of time, yes, I can see two. But within the coherence time of the pulse, I can only see one photon. So a source that emits one photon, one photon, one photon, one photon, exactly one photon in each. Boy, we would love such a single photon emitter. That would be a great source to have for fun and profit. But that's not what thermalite is. Thermalite has actually there's more chance of seeing two photons within the same temporal mode than to see them far apart. Okay. Now that photon bunching, that photon statistics, in this case, is coming from, we can think about it in two different ways. One way that we described it over here was this. The excess of this over that was intensity fluctuations. The excess intensity fluctuations was why this was bigger than this. If I had no intensity fluctuations, we had this flat line. But from a particular corpuscular point of view, it's bosonic enhancement. I heard about bosons and fermions and Maxwellians. The fact that you're going to likely to see two photons in a mode is because of Bose statistics. It's because the two photons want to be more likely in the same mode. And in the thermal state, that's what they'll naturally do. You'll naturally have more photons in the same mode rather than separated. At the level of the field, it means excess amplitude fluctuations. At the particular level, it means that there's more likely to be two photons in a mode. It doesn't mean that we can't engineer states of light that don't adhere to what natural thermodynamics can do. We can do that with a coherent state. A coherent state isn't bunched at all. It's neither bunched nor anti-bunched. It's completely random. But if we had a non-classical source of light, then we can see photon anti-bunching. So to answer your question, Benny, why do we need the quantum theory? So non-classical light, we had two signatures. Sub-Poissonian statistics, meaning that in a given mode, the fluctuations in the number of photons are less than n. A Fock state is an example of that. And photon anti-bunching. And this was the first thing this was the first experiment. This actually was done by the famous foundational member of the quantum optics community, Jeff Kimball, and his PhD thesis with Len Mandel were the first to demonstrate photon anti-bunching. And we'll talk about that maybe the last lecture of the semester, when we have to want to think about a source that could produce non-classical light. And one source of that is thinking about resonance fluorescence. So if I take a two-level atom and I drive it with Rabi oscillations, as we'll discuss soon, we can get spontaneous emission. Those spontaneously emitted photons come out anti-bunched because if I emit one photon, I'm back in the ground state. So there's no chance I'm going to see another photon until I absorb. And so there's no chance of seeing two photons within an absorption time, and the photons emitted in resonance fluorescence are anti-bunched. And that was the first example of seeing the photon statistics of non-classical light. So I'm going to have to run off because I have an appointment to go to, but I just want to conclude and we'll follow up more during the problem session. One of the things I wanted you to take away from all of this discussion is that the distinction between classical and non-classical light is not about the properties of individual photons. We can see everything we can explain in terms of seeing a photon or not, one photon or not. We can understand in a classical way with quantum matter explaining the fact that I have discrete jumps. The non-classicality is seen in the photon statistics. The photon statistics are about the fluctuations in the number of photons or the correlations between photons. And it's those features that can have non-classical power. And the non-classical power that we might want to use for things like quantum communications, quantum sensing, quantum computation. It's the statistics of the photons that are important. And that's what and we'll see more of that in the times to come. All right. Very good. We'll conclude there. I have my stuff. I've got to run to my doctor. Have a good afternoon.